Hi, my name is Eugene Lee, and in this video, I'm going to demonstrate the project that I built for the Sensing Exploration Thread as part of the Georgia Tech DC Department's Ultimate Thread Challenge. To start off, what I built was a scaled-up model of a microelectromechanical altimeter, or MEMS altimeter. The inspiration for this came from the fact that I had a lot of experience working with altimeters in the rocketry clubs I've been a part of, and I felt like this challenge would be a great opportunity to go deeper and learn more about the underlying sensing mechanism by building my own physical model. First though, a quick explanation of how a MEMS altimeter works, using a video made by Bosch about their BMP390 MEMS altimeter. An altimeter has two key components, a pressure sensor and a separate signal processing circuit that interprets the sensor's outputs. The pressure sensor itself works by using 4 resistors attached to a thin membrane that change in resistance as the membrane deforms. The bottom of the membrane is sealed, while the top is exposed to the surrounding air. So, as the altitude changes, the difference in air pressure between the two sides of the membrane creates a pressure difference and therefore a deformation in the membrane that can be determined by measuring how the 4 resistors' resistance changes. This configuration is exactly what I based my own altimeter off of. This thin metal sheet acts as the pressure sensor, and these two devices here are the signal processing unit. This HX711 is an ADC that also amplifies the signals from the sensor, and this ESP32 does all the calculations, converting changes in pressure to changes in altitude. And here on the sensor, I've got 4 strain gauges arranged in a 4-wheatstone bridge, all covering an airtight container. The ESP32 has Bluetooth capabilities, and so I also programmed my own iOS app to interface with the altimeter and make it easier to control and visualize the data in real time. Now, I'm going to demonstrate an actual BMP390 in action so that we can compare its behavior to the one I built myself later. This is a PCB flight computer I built previously with a BMP390 attached to it. As you can see, as I move the device up, an increase in altitude is recorded. And as I move it down, a decrease in altitude is recorded. Next, I put the BMP390 in an airtight container, with a syringe hot glued to it so that I can easily simulate changes in air pressure and therefore altitude. As you can see, the expected behavior again occurs. When I pull the syringe up, the air pressure inside the container decreases, and so the BMP390 measures an increase in altitude. The opposite thing happens when I push down on the syringe. Air pressure increases, so a decrease in altitude is measured. Note that with an increase of around 30 milliliters in total volume, the BMP390 measures a roughly 150 meter increase in altitude. And now, I'm going to demonstrate my model altimeter in action. Unfortunately, it isn't as sensitive as the BMP390 is, meaning that it can't measure changes of it moving up or down a couple feet. I have to put it in the test chamber to produce measurable results. Another difference is that it takes a bit of time to calibrate and wait for the data to stabilize before sending any readings. But other than those two things, my model altimeter has the same behavior, in which a decrease in air pressure corresponds with an increase in measured altitude, and vice versa. In addition, you can see here that I managed to get the same increase in 30 milliliters of volume to also correspond to around a 150 meter increase in altitude, though it isn't always consistent. Here's a video of a different trial with the same increase of 30 milliliters corresponding to an increase in 190 meters. And here's another trial where it's now 230 meters. Now, I'm going to run a trial directly comparing the BMP390 with my model altimeter. I turned both on and put them in my test chamber so that they experience the exact same conditions. As you can see, my model altimeter has the same general behavior, but the altitude measured deviates in magnitude quite a bit from that of the BMP390. This huge variation has a couple of reasons, the biggest one being the nature of the metal sheet I'm using. It's not perfectly elastic, meaning the way it deforms can be very unpredictable. In addition, there's also just a lot of noise in the signals because the components I'm using aren't the most high quality. On a side note though, because the altimeter works by measuring changes in the shape of the metal sheet, it means that if the data processing algorithm gets changed, it could also be used as other sensors like an accelerometer, or even just a plain scale. Yet overall, Even with all these areas of improvement, I'm happy with how my project turned out. My goal wasn't to build a precise altimeter with actual applications, but rather to create a hands-on demonstration of how MEMS pressure sensors work. The device clearly behaves according to the correct physical principles, which I consider a success given the amount of money and time I invested.
More importantly, this project helped me learn more about how sensing technologies work, and made me appreciate the sensing exploration thread more, and I hope it will do the same for any viewers. That's it for this video, thanks for watching.